Hi, everybody. Welcome back. Happy Monday or something. Today, I want to talk about my love-hate relationship with types. And I'm going to take us down strange and curious space, I think. And perhaps most importantly, I'm going to have us discuss some stuff that I could use your help on, because I don't think I actually know the answer to this. Well, I don't know the answer to many things, but this one in particular is a doozy. It's a bit of a thorn on my side. And I've thought about this deeply. And when I say, oftentimes when I am working with new students or new folks, I'll say things like, yeah, think deeply on complex problems. And then after maybe like a few minutes, they'll say, okay, I've thought deeply on this, and here's what I think. And I'll say, no, no, what I mean by think deeply is maybe marry yourself to this thing over the next several years and look at it, think about it, work on it. Just embrace this concept and explore it in all these different ways so you can try to get at the heart of its strengths or its weaknesses or whatever. And so when I say that I have thought deeply about something, minimally it usually means I've thought about it for probably weeks. In some cases, I mean that I've thought about it perhaps for years. And this is one of those cases where I have thought about this, specifically types, data types, for years. And I'm very conflicted. The short of it is, on the one hand, I think type information can be super valuable. And it can be really valuable for things like compiled languages, pushing runtime errors to compile time, clarity of understanding of what's going on in code, and therefore abstracting types out can oftentimes make the code more ambiguous, more confusing, and not necessarily so great. For example, come on, buddy. Come on. Bro, come on. Really? Come on, buddy. Get over here. We got the dog. Come on, buddy. Come here. Show everybody you're here. Come here. Come here. Come on. There you go. You almost made it. Come here. Show everybody. We got him. Let's hold him hostage now. Okay, you made an appearance. No face kisses, okay? Just chill. Okay, so part of the thing that I have here is C++ auto, right? And for those of you that don't know, this essentially is C++'s way of saying, hey, we'll figure out the type automatically for you. Don't sweat it. And I think there's certain restrictions. Auto doesn't work in all places. You gonna stay here, buddy? Or are you gonna make a, there you go, just stay right there. Yeah, just chill. I don't know the ins and outs of auto. I suspect that there's limitations on how it can be used. And I've used it in some cases. Principally, I use it for iterators. STL containers that also have complex types inside of them. And then referencing the iterator or like constant iterator. Oh boy, this is like 80 things long, 80 characters long. And using it for that, I think, is a delight, purely just to save me from typing, especially if people kind of know, like for auto iter equals this container dot begin or something, right? And stick around, buddy. And so in cases like that, I think auto can be helpful. But I've also seen people go a little bit crazy with auto in and making code that would otherwise be like readable and understandable, now a bit obfuscated and hard to understand. So I'm conflicted, right? On top of that, in a very simple analysis of this space, if you're doing rapid prototyping, like one might do with Python, one might even argue with things like JavaScript, although I think that JavaScript can be used for production code quite a bit, and I think therein lies a little bit of the challenge I have. And I also think that that's why TypeScript could be beneficial. But if we stick with rapid prototyping, let's just say Python. Great for rapid prototyping, but then maybe not fast enough for like production code. And so then once we get like proof of concept through this, we can upgrade to this. But so in rapid prototyping, types can slow you down for sure, right? Just figure out all the types and just do the right thing. Like, I don't have time for this nonsense. And as a researcher, I think writing prototypical code for research ideas is a great way to quickly test things out. And doing that in Python or other environments, Lua, it can be a massive time saver, because the time that is spent is perhaps the majority of it is on quickly cranking out a system to demonstrate its viability, right? Let me close Slack here. So I get the value of not having types. And I don't even want to open up the JavaScript, TypeScript can of worms yet. But on the other end of this spectrum, you have production quality code. And I think types can really save your life. And when you get to systems that are multi-million lines of code, I think there's a reason why most of those systems are somewhat strict typing. Strongly typed, as some say. And what is a strongly typed system? Let's not go down that rabbit hole, but let's just say there are systems that if you have, let's say, systems that require type information for data structures. That's we're going to call it. That's not the precise definition, but the precise definition of like strongly typed languages versus like weakly typed, it's actually not nearly as clear as I think some people pretend it is. And if you don't believe me, some of my slides from one of the years at the university talk about this, and it is a bit of a rabbit hole. Okay. But what we're talking about here is for these production quality systems, when you have millions of lines of code, types can actually reduce the errors significantly. And you really want, I think, in some sense, types, because they can just do sanity checks. Like, is this assignment actually valid, or are you trying to assign a floating point number into a string? And maybe that's even allowable. Maybe you should be able to do that, but maybe you should specify that, hey, I mean to assign this floating point into a string and convert the floating point thing into string. Like you should say, yes, cast this into a string, right? Rather than the floating point number is being assigned to the string, right? String stir is equal to FP or something. There's various ways to kind of indicate this rather than having like implicit type conversion. Okay. So this is kind of like the high level discussion. And again, keep in mind, this is like I was saying before, this is something that I've thought about deeply. And when I say deeply, I mean like I've thought about this for decades, maybe. I also want to share that we're going to talk about Hans Boehm, Professor Hans Boehm, and we're also going to talk about Professor Jeremy Siek, Goju's PhD advisor. In fact, I think that I was Jeremy's first PhD student, I think. And it will become apparent very quickly why I'm talking about these two gentlemen related to this topic. But before we go down that, the last piece I want to add is this is the simple discussion. This is the discussion that most people find themselves in. And the truth is, I don't really care about this discussion that much. I'm just adding these brackets because it's fun. I do this kind of thing in Notica. At some point, we'll show Notica and you'll see this kind of thing. I don't know. It just like makes it prettier. So, it's not perfectly aligned. There we go. Okay, there we go. We need to have those colons perfectly aligned. This is Goju's OCD kicking in. Okay, so this is like the typical JavaScript, TypeScript, C++, whatever debacle, and you have people like I think DHH talking about how TypeScript is the bane of everybody's existence, which I'm not sure I agree with, but I can understand. I mean, I've read some blog posts, and I think it's a little too much of this and not enough of this. And again, I try to use a lot of this. This is really where I tend to live. I just want to figure this stuff out. And this is not a religious thing for me. Like, in fact, I think DHH was talking about how types, whether you like types or don't like types, it's like a religious battle, and you have people on either side, and their opinions never change. Well, first of all, if that's the case, I don't fall into that category because I see advantages to both sides. In fact, I think that not having type information for things like rapid prototyping and languages like Python is a huge boon. It's part of the reason why I think that language is so easy and so accessible, is that much of the type information can just be automatically inferred. And if you don't need the system to be screaming fast, and it's going to be small, and by small, what I mean, just to give context, I mean, essentially, so when I'm talking about rapid prototyping, here's what I mean. I'm not saying this is like a bragging thing. I just want to help you understand the way I'm thinking about this. If this thing is less than 100,000 lines of code, I think it's kind of like a prototype. And I tend to think of production as being in this space. Okay, so, and then there's stuff in the middle here. This is like I don't know what you are. You're not really a prototype, but you're not really like a large scale system. This is not totally true because I think Git is maybe 500,000 lines of code, but I'm just trying to draw the distinction that I think rapid prototyping stuff, like for example, Urs, no joke, when Urs understands a system really well, he could probably crank out 100,000 lines of code in just a couple weeks. For real. That dude's like, he's an alien. Okay. He thinks in code. And I mean that with the highest regard of respect, Urs. So, and I know other people that are good, maybe not to Urs's level, but very competent programmers that can also crank on stuff. And so I don't think of systems that are like less than 100,000 lines of code as sort of this, like, it's going to be a system that runs the world. And it could be, but it's just so tiny. Like, it could be a library, right? But those systems tend to be so simple that type information is not, I don't know that it's needed. And again, I'm not trying to sound arrogant here. I'm just trying to help you understand how I think about these problems. Because I think when Notica got to over 1 million lines of code, I couldn't keep all of the stuff in my caches. Couldn't do it. There's just too much stuff. And so types really helped me. When it was 100,000 lines of code, I kind of knew everything. It was just like, you could delete all the types and I could still see all of it. So this, I think, is one of the key distinctions, is as you get these more complex systems, having type information can really help you. And this isn't a universal thing. If you have a critical system that's like, flying a spaceship or running a hospital, or it's controlling a power grid, yeah, you probably want types in there, because even if it's 1,000 lines of code, you want the compiler to help you, right? That's basically one of the key things that I think has been lost somewhere along the way, is compilers are not your enemies. I think that compilers are your friend. And they only feel like they're your enemies when you first start working with them, because they're telling you a whole bunch of stuff that you probably don't want to hear, and it's making your life more painful. But they're like the good parent. They're like the good mom or dad that's like telling you need to eat vegetables. And they keep complaining until you do. And then 5 years later, when you've got the habit of eating vegetables, you're super thankful that mom and dad were telling you, eat your vegetables. It's the same thing. Same-ish thing. Okay. So this is the simple argument. And frankly, I don't even really care about this argument. This is not why I'm concerned. I'm concerned about it because of this. And we're going to get a little bit into this. But as I think about machine programming systems, the systems that are going to, I believe, in the very near future, help us run the world and create software that is vastly more complex than the software we have today, these MP systems are going to help us in ways we can't even fathom. I think that it's very much like the internet. When the internet was first coming out, we couldn't even begin to reason about the complexity and the excitement and the value that the internet would provide until we got the internet in front of us. It's very much like Mentor, right? Like we're building this. Oh, by the way, this is my advisor, Jeremy, super awesome guy. By the way, so you may wonder a little bit about me and how Professor Siek and I got synced up. So he's the author of the Boost Graph library, really well respected and well known in C++ community. I think he's one of the original inventors of this thing called concepts. It's been a long time, so I'm probably getting this wrong. But basically the idea is, if I'm recalling correctly, it's to reduce the error messages that you would get with templates. Because just like me, and I think, I don't want to speak on behalf of Jeremy, but I think Jeremy also has this complicated relationship with types, right? I mean, he invented gradual typing. It's like he and I forget the guy's name. Let's look him up, actually. It's like Wadi Taha. I'm getting that wrong. Walid Taha. I think University of Edinburgh, or was. Let's find out. Oh, okay. Was he? Taha. Okay, I have to know. Am I really getting that confused? It's entirely possible. I was talking with Taylor earlier today. I mess stuff up all the time. Okay. Meta? Okay, hold on. This is... I thought... Hold on. Am I getting confused? That's entirely possible. Okay, gradual type... Okay. Find... I'm getting confused. Okay, cool. Sorry. This is one of the papers. Keep in mind, like, it's 20 years, right? Because this is 2007. And I was working with Jeremy during this time, but he was doing other work. And I think that it's... you can maybe see the confusion. The W. Okay, so I think this is our guy. Let's see. Philip Wadler. Okay. Any bets on University of Edinburgh? Oh, victory. Okay. All right. So I knew that there was a super. Okay. So this is what happens when you survive on 3 hours of sleep for a long period of time. And two people have the letter W in their name. It's in my defense. Look, I'm owning the wrongness here, but it's not that common of a letter, right? So that's where my brain went. Anyway, I think that Jeremy was working very closely with Philip Wadler at the time. And and again, I'm probably getting a little bit of these details wrong. But blame for all. This might have been let's read this. Several programming languages are beginning to integrate static and dynamic typing. Yeah. So this already is moving down the gradual typing. Okay. The reason why I'm able to sort of draw this conclusion so quickly is when I think about gradual typing, at least in my naive perspective, and I didn't invent gradual typing. Jeremy et al. Did, so I know very little about it, but I think of it as a fusion of dynamic type binding and static type binding. Dynamic type binding is binding of types that are happening at runtime. So I believe Python is an example of that. Maybe JavaScript is an example of that. And you can have, I think you can have weekly dynamic type binding or strong dynamic type binding. And I think that Python, again, don't trust me on this. I'm not an expert in and the knower of all things. Okay. I know a little bit about a little bit. So don't totally trust me on this. But I think that Python has strong dynamic type binding, which means when you do a binding of a type at runtime, then it's bound to this. And so if you try to then kind of change the type in a massive way, Python is like, whoa, you can't really do this. Fact check me and tell me that I'm wrong in the comments. This is one piece of 1,000 that we're going to discuss here. So I don't want to go down 300 different rabbit holes. We're going to get out of the Milky Way into other parts of the universe if we do that. Okay, so let's say that that's what Python is. Let's just pretend if that's not reality. Then you can have other languages that don't have strong dynamic type binding. They can have weak dynamic type binding. And what that can mean is you can bind to a type, and then they're used for that type in this context, and then they can just change to something else. And so it's weak. It's not like strong in that it's fixed. So there's like a bunch of different ways to do this with these dynamic systems. Now, with static typing, you also sort of can have this idea of weak and strong static typing. And again, I don't want to debate the origins of these words, but let's just say for our argument that the strong type binding is when you have something be a type, then it kind of is going to remain that type from the compiler's perspective until you sort of force it to be another. So it goes back to the casting. So let's say something is a string in the static environment, so it's compiled, and then you try to assign it a floating point. It's like, you can't do that. But if you can't do that implicitly, but explicitly, you could say, no, yeah, you do it, right? Or here's a conversion operator. And so it can call that implicitly. So there's ways to do this, but there are certain rules. And then for a weak system that is statically typed, it may just do all the stuff as long as it's within reason for the type system. And there can be all these kinds of rules and all these different embodiments, and I don't know half of them or any of them basically, but hopefully this gives you a sense. Now, when I think of static and dynamic, I tend to think of gradual typing, because dynamic type systems, generally speaking, don't require type information in the code. That's why they're dynamic. So it can kind of be whatever you want them to be, and the system is sort of figuring them out as things are executing, thus Python and JavaScript. But static type systems are just that, is now you have to tell what the type information is ahead of time to some degree. And so you'll have things like C and C++, or Java, or TypeScript, right? So when I see the fusion of these two things together, my head immediately goes to gradual typing. Going to be multiple things. Okay, now let's continue reading. Several programming languages are beginning to integrate static and dynamic typing, including Ratchet, formerly PLT Scheme, Perl 6, C# 4.0, and the research languages Sage and Thorn. However, an important open question remains, which is how to add parametric polymorphism to languages that combine static and dynamic typing. We present a system that permits a value of dynamic type to be cast to polymorphic type and vice versa, with relational parametricity enforced by a kind of dynamic ceiling along the lines proposed by Matthew and Ahmad and these other folks. Our system includes a notion of blame, which allows us to show that when casting between more precise type and a less precise type, any cast failures are due to the less likely typed portion of the ... Okay, so I look at this and I think that this is likely a thing about gradual typing, even though the name of it is blame for all. That's my speculation. We don't have time to read this, but the point is that Professor Siek and his colleagues care a lot about types and have been working in this space for a while, and therefore I've been also thinking about, I think this is maybe one of the, blame for all. Yeah, this is maybe one of the first ones. 3 sums with and without blame. By the way, I think that there was pushback on the title of this paper, as you might imagine. Oh, look, here's a familiar author. Yeah, cool. So anyway, types are interesting. And I think gradual typing is an example of how both dynamic and static typing can be important. Thus kind of the shift of typeless code in JavaScript to typed code in TypeScript. And it goes back to this concept. And again, I have done both of these types of systems. Doesn't make me an expert, just makes me someone that has done both of these types of systems. And my general view, and you can choose to believe me or not believe me, is I think that systems like this, you generally, when you're dealing with this much code, you generally want types because they can save your life. When you're dealing with this much code and you're doing this kind of thing, you oftentimes don't want types because they kind of just slow you down. I mean, if your goal is to just go as fast as possible and demonstrate ideation, like the practical viability of some idea that you have for a patent or research idea, yeah, I mean, just all that STL mumbo jumbo to like specify the iterator, and it's like by the time you get done typing that out, you feel like you've written like a full haiku, and you might have actually. Yeah, in Python, you don't write any of that. You just write like the name of the variable. So cool. Okay. So this is a little background on me and some of the folks that I've been hanging out with. And obviously I've had many very deep conversations with Professor Siek in his mentorship of me, which, by the way, he did an incredible job, so incredibly patient with me. I was wildly clueless, so incredibly clueless about research and how to think logically, rationally, like really as a scientist. And I learned so much from him. I'm like infinitely grateful. So thank you, Professor Siek, if you're watching this. All right. And then, as I think many of you know, I love templates. I love templates. And part of the reason why I love templates, which is kind of interesting, and keep in mind, this guy loves templates too. And the way you know that he loves templates is he wrote this book. And he built this whole library, and this whole graph library thing, to the best of my knowledge, is basically it's written in templates and it's using generic programming, which is kind of amusing given that templates are abstractions. They are algorithmic abstractions eliding away type information. See how this is working? Do you see where we're going with this? Is that one direction, we've got types, and then it's like, wait, having types is making things less, it's preventing things from generalizing, so get rid of the types. That's C++. That's C. C++ templates, C void pointers. By the way, for all the C people that are watching this, I love you guys, but come on. Seriously, templates over void pointers. I mean, void pointers are just super powerful, but wow. Okay, so that is an example of specificity to generalizability. And then JavaScript is JavaScript will say is the opposite. It is generalizability to specificity. JavaScript to TypeScript, right? So they're doing both like opposite things. And I think Jeremy was seeing this in his head, coming from both sides, saying, whoa, there's this really interesting fusion. And I agree with that. Now, one other person I want to talk about is Hans Boehm, who I also got a chance to collaborate with. And we've got a thing here. So Hans and I did this thing, wow, 12 years ago. Yeah. And Hans and I both love templates, and we both loved transactional memory. I still love it. I just don't want to speak on behalf of Hans, but I'm pretty sure that Hans still loves this. So in my travels, I met Hans, and I quickly realized that he's incredible. We're actually spend a little time. I want to spend a little time just showing you a little bit about him. I mean, he's on another level. Again, like I was saying, I've been very blessed to work with some really incredible people. I mean, yeah, like this guy has a garbage collector named after him. I mean, that's pretty cool. Yeah. How many people have a garbage collector named after them? I mean, I don't. So that probably tells you something about its pervasiveness, its ubiquity. So anyway, Hans is an extremely intelligent guy. Also, one of the most soft-spoken and humble people I've ever met and worked with. And it's doubly amusing because Hans is like 6'5" or something. He's really tall. He's really tall. And he's just very soft-spoken and just very kind. He could be wildly physically intimidating because he kind of like towers over everybody. But he's not like that at all. And I was noticing something on Google Scholar is, I think some people care a lot about this H index thing. And I got to tell you that I think Hans Boehm is not one of those people. I also don't really care. I mean, I don't know. It's what do they call it? It's like a bean counter, but whatever. I care more about doing important work than having a whole bunch of papers that have been cited by a whole bunch of people, because I just find that, yeah, oftentimes somewhat hypey. Like, for example, how many times has the original Transformer paper been cited? Or how many times, like, I'm on the program committees for like, so I'm on a lot of, I think I'm usually on 5 or 10 program committees every year, and I continue to be on many of them. Although I got to be honest, I haven't said yes to this one yet, and so I've been part of this one for many years, and I quite like NeurIPS. I think that it's really good, but I'm really going down some rabbit holes. What I don't like is when the area chairs do not listen to the entire group of what seem to be objective reviewers' feedback that's coming in uniformity. There's 5 of us, and we're all saying, don't accept this paper. It's not good. And then we get overruled because the area chair is like, well, I'm accepting it. And it's not great. And it's especially not great when it feels like it's politically motivated. I really don't like that. You know, that's the reason why I'm on these program committees is, one, I like to learn. And so I try to only accept the papers that I think, oh, this is going to be really cool. I'll learn something and I'll get a sneak peek of a paper that's probably going to be published anyway. And sometimes I'm lucky and that happens. And then I also like to help, right? Like, I think sometimes people have really good ideas, but then maybe the writing is, you know, or the story needs a little work, or they need more experimental data, you know, so we can, you know, I've shepherded many papers, if that's a word. Anyway, what is the point that I'm trying to make here? Oh, yeah, so I'm on a lot of these program committees, and I enjoy the service part, and mostly I just really like to learn, and it gives me the opportunity to think about complicated things. And you really have to pay attention. I can't skim it. Otherwise, I'm like, what am I doing? Right? I'm not helping and kind of doing a disservice to the authors and stuff. But in recent years, there's been so many submissions to NeurIPS. They've been starting to do some stuff that is, I think, somewhat questionable. Like, we'll not get into this in this VOD, but the higher order bit I think we're going on is Hans, very much like other folks that I think are here to do like really powerful work. I don't know that we really care about this thing. That it's something, but there's so many other things that I think are far more important. And I wanted to mention that because I think Hans used to be a professor at UT Austin, and then he left there. I think he joined Google, and I think he's been at Google since. But Hans is the kind of person that those of us in the community, he's unparalleled. I mean, he like, when Hans talks, everybody shuts up. We all just shut up and listen to what Hans has to say, because generally speaking, when Hans says something, he's right. He's right before everybody else in the room is. I think he's the one that wrote this paper, There's No Such Thing as a Benign Data Race. And oh my gosh, like, I remember reading this paper and thinking, holy cow, how could he figure stuff out like this? Where is this? Benign. Yeah. Oh yeah, this is such a beautiful paper in my mind. And also Hans is just such an eloquent writer and speaker that, yeah, so I encourage all of you, if you haven't seen this paper and you're interested in knowing more about data races, how to miscompile programs with benign data races. Whew, such a doozy. I then started to quote Hans when I would have discussions about people saying, well, it's a benign data race. And I would say, Hans says there's no such thing as a benign data race. And then oftentimes that would be sufficient. People are like, oh, Hans says that? It's like, okay. So if Goju says that, nobody cares. But if Hans says it, then okay. Anyway, so at some point, Hans and I start hanging out and doing stuff together. We worked on transaction memory for C++ and part of like SG5. I absolutely love this guy. I really wish we had the opportunity to do more work together. But then, yeah, he moved from HP Labs to Google. And yeah, it just wasn't as smooth, I think, of collaboration. environment with the new stuff he was doing at Google. Irrespective of that, we started to do this generic programming needs transactional memory, and I wanted to raise this because the motivating example of this was this type of thing to show essentially that if you have fine-grained locking and you try to use fine-grained locking inside of templates, that there's sort of no provable way that you can make the code deadlock-free. This is what Hans and I try to demonstrate. Like, I don't know that we proved this, but I think that with the one counterexample, I think that this was fairly compelling. I don't know. We published this at Transact, and then we both got busy with other things. So this was never like a full conference paper or anything. But we then showed that if you took basically the same generic system and used transactions, that you could make things work. Okay, so how does this relate to types and yada yada? Okay, first, we're doing type abstraction here with this template, and this is actually critical for this example. What's interesting is that when you think about locks, one could think about locks as, especially fine-grained locking, not coarse-grained locking, you can think about them potentially as being something that has a high degree of specificity, because that's sort of the difference between fine-grained and coarse-grained locking, right? Coarse-grained locking is meant more general, like the single global lock or whatever they call it in Python, versus fine-grained locking that, and I think they're, yeah, something like that. So when you have locks, you can think about them as they're like super specific, and it could be that part of the trick here is that templates themselves are abstracting out to be more general, and fine-grained locks are inverting this to be more specific. Hopefully this is making sense. And if it isn't, I apologize. My tablet's around here somewhere. Maybe in the next episode I'll like draw a picture. But I think some of you, I'm fairly certain, interpretable metaphor is 15 steps ahead of me already. Okay, so now we move to transactions. Transactions, unlike locks. So think about what I was just saying about the fine-grained locking. Fine-grained locking, locks essentially have names. They have specific names, and those names define properties implicitly in the program, like the locking order. So lock 1 has to be done before lock 2. And so that naming thing could be considered like specific invariants in the code that are, it's almost like they're almost like they're types. Not exactly, but almost like they're types, because they are defining rules and properties of the behavior of the program, very much like how types would be, right? But transactions don't have names. Transactions are abstract concepts like generic programming. So is it the case, and again, we're hypothesizing here, I don't know the answer to this, I'm just going into crazy abstract scientific thinking here, we're pontificating, this is like a thought experiment. Is it the case that what's happening here, why this actually works? So we just maybe take my word for it. This works and this doesn't. You can read the paper if you don't believe me. And Hans Boehm is the one that came up with this, who's way smarter than me. And he spent deep time making sure. Like, I'm not saying that Hans is perfect, but this guy knows what he's doing. And I also was involved. So what we attempted to show is that this code definitively deadlocks and this code doesn't. Because of the properties of transactions and because of essentially their generalizability, they don't have that specificity property, which is not even like a clear thing in terms of like the definition of transactions. It's like one of these abstract implicit properties that nobody really talks about. It's sort of like how we talk about fine-grained locking and people talk about locks, but they don't talk about how locks have names, and the names of locks are the things that dictate the locking order. And as long as everyone always follows the same locking order, you will avoid deadlock. Like that's the fundamental invariant you can't violate. Principally, this is like, at least as well as I understand it, this is the property you have to maintain. And transactions don't have names. They are a generic construct, very much like templates. And so what's happening is you are having two things, two idioms that are both functioning at the same level of abstraction in some sense. The abstraction is they're both nameless. They're both typeless. Okay? And now you might see where I'm going with this whole type thing. Okay. This is the beginning of the discussion, but I want to wrap this up just because I feel like an hour is long enough. So this is the fundamental background of the story. But now why does this impact machine programming? Okay. This is the part that really makes my head hurt. All right. Or at least makes me deeply ponder about things. I'm really interested in reasoning about code. Super interested about deep reasoning of code. This is, I think, git slash. Okay. Sure. Okay, I'm just picking a file here because I want to show something. And this is just an arbitrary file, so I have no idea what we're going to find. But I suspect we're going to find something that is meaningful. Okay. All right. I'm going to try to find something that has a certain degree of concreteness that then I can, this is just going to be a good piece of code to demonstrate this point. So just, I actually saw a couple. Hey, look, is racy. Okay. I want to take this one just for argument's sake, just because this may drive home the point to some degree. We're going to maybe look at a good example and maybe a bad example. So this will be maybe the good example. Okay. With machine programming systems, there's many different phases of the systems, but one of them is learning from code. One of the most important questions that I struggle with MP systems and learning from code is the question of whether or not type information is helpful or hurtful. So let's think about this for a second. Is type information helping the MP system learn, or is it hurting the MP system from learning? Now, in this example, we have types, int, const char, all of this stuff, and then it's going to do something. So if this code is processed the way that it is, the MP system could, by default, include the type information and then learn about this behavior and then think that what it's learned is specific to these types. But now let's ask just a very simple question. What if this were a const str, like a const stood string, not a character pointer? And then the same thing is done here. Do we think that this code is going to sort of work? Well, we can imagine that this name compare thing could work with two strings, stood strings, rather than char pointers, right? And then if it could do that, then the rest of this seems like this could probably work. And now it works for two types of strings. Okay, what about like W chars, Y chars? What about Unicode? See where this is going? Now let's go further. Why just ints? What about longs? What about shorts? What about any size of an integer? Does it really have to be whatever the size of the int is? Or is this meant to be more just a generic type that is like discrete numeric? Very much like this is meant to be just sort of like a string placeholder, right? So now imagine that this code was rewritten to where the types are placeholders to represent semantic information, not specific concrete types that may be too specialized, that work. They absolutely work, but they're conveying a concept that is more specialized than the MP system needs it to be when the MP system is learning on that code. That the MP system could instead either elide away the type information or create proper abstractions of the type information to higher order semantic concepts, like what we were just describing, discrete numeric type and general string type, and then just know that that is essentially a superset of all the different types of strings, what have you, and this other one is all the different types of discrete numerics. It's my belief that that MP system that could do that abstraction would learn more. And this is also why I tend to be far more interested in semantic reasoning and, in fact, semantic meta reasoning, which is way too complicated to get into right now. We don't have enough background to really discuss it, so we'll just put a placeholder. But if you're curious, I think I have some slides on my website where I talk about this sort of at the end of my course, and I probably need to create a second course, advanced machine programming, that talks about temporal analysis across the two axes, as well as meta reasoning. probably 3 courses. One that's just about the temporal stuff, and then another that is just about meta reasoning. Because meta reasoning is it's there's so many different things that you can reason about, but I also think it's extremely important as you start to learn intentionality of code, not just the semantics of the code, but the intention of the code. So, for example, as someone that's written a lot of code, what I believe they're doing here is what their intention is they're trying to write this cache name comparison function, and that it should compare essentially 2 strings and have these 2 discrete stages or something. That's it. And all the rest of the things are just byproducts. So like the len1 is probably just related to the length of this. Yep. And len2 is just the length. I mean, it's like you don't even need this. It's just a byproduct of the structure of the strings, I suspect. Again, I've never seen this code before, so what do I know? But maybe that's what's going on. And then these stages, yeah, I don't know what these stages are, but I think they're probably important. It's maybe telling you an order of things, who knows? But they needed a syntactic way to express these concepts. And so, because in C++, it has this is C, it has strict typing. So you have to have the type information to explain this, right? And so you do. But now in other languages, like Python or JavaScript or Lua, you could elide away this information and just have these variables. And now the MP system could actually learn potentially a more generic algorithm. This may also give you insight into why many of the simpler CodeGen systems work specifically in scripted languages that do dynamic type binding, because they don't have to reason about type information. They just are able to do essentially token prediction, keyword prediction, whatever, based on the algorithm. And if the algorithm is generally applicable, then the sequence of algorithmic steps, in theory, could be somewhat similar, right? Like a quicksort is, you follow the quicksort algorithm, and probably somewhere on the internet there's a pseudocode that has no type information, explains here's how you do it for any types, and then you just use that for like Python or JavaScript, and now you have insight into why many of the CodeGen systems only work for languages that have dynamic typing. And largely it's because they can't work at this level, because their systems can't learn on these specific specialized types. Maybe "can't's" too strong of a word, but I know the details of how some of these systems are built, and they're not. Many of them don't have programming language specific models, and that's problematic. Okay. I mean, I think now some of them are evolving, but yeah. So anyway, you can see the complexity here. Now, on the other hand, so that's the advantage of eliding types away to make things more generic and learning in a more generalized way. And in that case, it seems like it would work. But now, another example, which is the counterexample, is, I think, yeah, something like this. Now, I'm not going to get into deep details here. I'm just trying to make a high-level point. Maybe I'll use this one. Trying to make a high-level point, and let's just pretend that I'm right, just to make this argument simple. And even if it doesn't work for this case, hopefully you understand the point of the argument. The other example we saw, you can see in your head how you can elide the types away, make them more general, and then it should still work. Imagine now that you had an algorithm where you couldn't do that. Like this. Let's say that this mempool thing is very specific, and it has very specific memory pool requirements that are bound to this type. They are constrained. And in fact, I think I was noticing something, as maybe I'm just making this up, but I think that this is essentially their specific type that they've created, that it's designed specifically for the purposes of the use here in Git. Again, I'm speculating, but let's just pretend that this is the case. Now, if you tried to do the same type of type elision, this could learn the wrong thing. If you elide the types from this and try to say, oh, just for any memory manager, this will work, arguably it won't. And so your abstraction of that would break this. And so now what we have is a very complex situation where there appear to be certain cases where eliding away type information or raising the abstraction of type information can help MP systems learn in more general ways. This is my speculation. It very well could be that the type elision, whatever the word is here, I'm probably saying this wrong, elision, it could very well be that if those types are essentially native types, then it can be done in a general sense. This is my speculation, and I think this probably makes sense. Probably. Like all floating point numbers, whether they're floating point, double, whatever, they fall in this category. And all discrete type, discrete integers, they're in this space. And all string things fit in this space. Sure. But I think you could go even further than that. I'm not sure. And I don't know where like Booleans fit in that space. When you start to get into user-defined types, I think it starts to get complicated, but I don't know that universally you can't do type abstraction for user-defined types. So for example, you could have a user-defined type that is essentially a tree structure. It's going to implement a tree. And let's say that like this is what it's going to do. And it's going to have certain behaviors that are specific to its tree structure. Then it's also going to have the typical tree behaviors that you see in all trees. If that's the case, then the semantic reasoner, the semantic learner, should be able to learn in an abstract sense on the general tree behaviors and then specialize for the specialized tree functions, methods, whatever, in this thing. How can it do this? Well, I think it can do it kind of the same way that humans do it, is we have this notion of a tree, and we see that. So when I say tree, all of us computer scientists think, oh, I know what that is. It's got this root, and it's got these things. And then I say, but now let's make this a binary tree. And now in your head, you're like, oh, binary tree, right? Okay, cool. And then I say, now let's make this a balanced binary tree. And oh, okay, yeah. So, but notice there's core properties with all trees that we understand. This notion of it, there's no cycles. It has to be acyclic. It's directed, right? These kinds of things. So similarly, I think that there's a space even for user-defined types where we can have core properties of these types that are somehow learned in a general sense from the MP system, but then the specialized pieces are off into their own little world and then do kind of like the specialized thing. Now, I don't know how to do this. Let's just pretend that I don't know how to do this, but I truthfully don't know how to do this in a general sense. I think I have some idea, or we have some idea on how to do it in like a constrained sense, but to apply this generally across all programming languages, this I don't know. I also, what I seem to think, this is my speculation, I don't have like a formal proof or anything, and I really want to hear what all of you think, is what's tricky about this is I think it's very much like Jeremy's gradual typing. I don't think it's an either or, because I've gone down this rabbit hole in both directions. I've gone down the idea of like, I think we should get rid of all types. And then I walk through what would it look like if we learned with all type information being gone. And in some cases, it's super great. And in other cases, it's completely horrible. And then I do the opposite. And I say, I think types should exist everywhere. And so we should have types in all things. And I start doing the same thing. And in some cases, it's super helpful, like potentially this case. And in other cases, it's like, why are you doing this? You're actually making the system memorize stuff that it shouldn't memorize. So therein lies the problem. I think this is going to be one of the keys. This is like semi-trust as far as one of the key things to learn. And I think one of the core pieces to make this really valuable is, or like really practical, is finding out how to do this based on semantic information in the code. That I think that in order to understand what type information should be present or should not be present, I speculate that if the learner can reason about the code semantics, then those semantics could give some indication on whether the type information should be present or not present. I'll leave you with that. If that doesn't make sense, we can dig in deeper. If it does make sense, great, you can start thinking about that. But hopefully this wasn't too confusing. But this is maybe the first episode where I decided, what the heck, let's actually start getting into some of the challenges that I think are real open challenges in machine programming, and stuff that I think if we can start chipping away at, I think we can start to build machine programming systems that are going to start doing the things that I see us using as real tools, real systems, not this vibe coding mumbo jumbo nonsense. I'm talking about systems that actually add real value. Okay. Thanks, everybody. Share all your thoughts and things in the comments.